Okay, so the next speaker is Rivu Bardhan, and he will speak on higher genus angel surfaces.
Uh, Thank you. First of all, I would like to thank the organizers for giving me opportunity to present how to work here. So, title of my today's presentation is Higher Genus Angel Surface. It's a joint work with Professor Biswas, Professor Fujimori, and Professor Kumar. So, yes. So this is the basic structure of the talk. So let's start. So for me, minimal surface is a zero-mean curvature surface in the Euclidean space. We have example like catenoid plane, helicoid, etc. So any minimal surface attains a sustainable representation. What is that? At if we have a Riemann surface M, I mean over function G, and holomorphic one from eta, such that these conditions are followed, then our minimal surface can be expressed as this immersion from M to Euclidean free space. Okay, so this triple is called the Wester's data of the minimal surface, and these are the examples of the basic minimal surface with the Wester's data. Okay, so in general, this minimal surface can be anything, but if we add two words, completeness and finite total curvature, the Riemann surface turns out to be a compact Riemann surface with finitely many puncture. And these G and eta that can be extended to the whole of the closure of the M. What is that completeness and finite total curvature? So this is a Riemannian metric on the Riemann surface. So the minimum surface is complete if this metric is complete on M. And the total curvature is defined like this, where K is the Gaussian curvature. So actually, from Osserman's theorem, whatever I stated just now follows. So for this complete finite total curvature surfaces, we have this inequality, Chernow-Osserman inequality, where n is the number of punctures and p is the number of genuses. Okay, so in general, this total curvature can be negative. So we cannot talk about lower bound. But if we define this absolute total curvature, then we can talk about the lower bound of this absolute total curvature from this inequality, which comes out to be this. So the question is, can we attain this type of surfaces which attains this equality? So yes, so this is the general question for if we have genus P and number of ends n. So can we make such surfaces? So it turns out that, I mean, in general, the question is still open. For n is equal to 1, the answer was given by Sato. And for n is equal to 2, for Fujimori and Soda partially answered this question for even genus surfaces. Okay. So what is remaining for n is equal to 2 case at least? So Weber constructed some surfaces numerically. He called them angel surfaces. It is a catenoid end and an n-aper end, and increasing genus. So for every p, numerically he constructed those. So odd genus, even genus, both. Yes. So the question is now, are these surfaces truly minimal? So let us see that. Fujimori and Soda conjectured in their article that yes, they are minimal, and this is their Wester's data, G, eta, and MP. We have some existence of these AIs. For this is the Riemann surface, and this is the Wester's data. Okay. So the genus 1 case of actually solved by themselves, but for the higher genus case, the problem remains open. So in the following slides, we will outline an approach to tackle these cases. Okay. To that, I start with a successful map. This map actually sends the upper plane conformally onto the interior of the polygon in C. It might not be a good looking polygon, but any polygon would work. Where infinity can also be one of the vertices. And further, this map also sends the real line to the boundary of the polygon. Okay, so this map has this format. So we start with a constant c greater than 0. We start with a ordered subset of real number and a subset of rational numbers. Okay, so then we define this map. Okay, so this set T is called the vertex set, and the A is called the vertex data. At the infinity, which can also be one of the vertices, we define the vertex data to be this. Okay. So now, a generalized orthodisk is the pair H with the metric defined from the Schwarzschild map. We can uniquely identify that generalized orthodisk by this tuple CTA. T and A are called the vertices and vertex data. So H union R, the upper plane with the boundary, with marked points at T is called the conformal polygon. And if T naught is a non-empty subset of H union R, I'm sorry, T naught is a non-empty subset of T, then H union R with marked points at T naught is called the enhanced conformal polygon. And this tuple is called an E-generalized orthodisk. Okay, so from an orthodisk, we can always generate an hyperbolictic surface and monomorphic form. How? So suppose this is an polygon. This is our upper plane. So this is our generalized orthodisk. The bold points can be conformal polygon or essential conformal polygon also, because it's we can take the whole set as a subset of the main set. Okay, then we can double this upper plane, and since this f star dz actually takes real number here, so it can be extended to the whole complex plane, and then we can branch at these bold points, which are elements of the conformal, essentially conformal polygon, and take the hyperbolictic copper. Okay, and the cardinality of the essentially conformal polygon actually determines the genus of the copper. Okay, and by pulling back the omega to the surface by the natural projection map, we can get a Riemann surface and a form. So okay, now suppose we have two such orthodisks which has conformal polygon as the same. So the genus, which is entirely, I'm sorry, two conformal, we have two generalized orthodisks which has the essential conformal polygon cardinality as the same. Then the genus of the two Riemann surfaces would actually be the same. So they would be actually same up to the homeomorphism. So there we can talk about a common homology basis and talk about the period of that common homology basis along the two forms. These two, for two orthodisks, we have two forms. So we can talk about the periods. Then we can compare the periods. Okay. So if the periods comes out to be conjugate to each other, then we call the pair of E-conjugate orthodisks of genus P E-conjugate generalized orthodisk. And if for the two E-generalized orthodisk, if we have same conformal polygon as well as the same essentially conformal polygon, then we call the pair as E-reflexive pair of genus P. Okay, and okay, these are all done for these odd cases where the essentially conformal polygon is odd. Okay, so yes. So this is my roadmap. So we'll first, try to choose a pair of E-conjugate orthodisk. We'll check in this set of E-conjugate orthodisk, does there exist an E-reflexive pair? If yes, from there we'll define the minimum surface. If no, we can comment no such surface exists. So I'll start with this. Basically, I'll assume that yes, irreflexive pair exists, and from there, can we define the minimal surface? So let's X1 X2 be an irreflexive pair, and AB with the vertex datas. If the vertex datas has this relation, then we have a form on the common Riemann surface. So when we have irreflexive, the irreflexive pair, then we have the cover as the same up to biholomorphism. So on that common Riemann surface, we have existence of this form. Okay, and from the conjugacy condition, actually from the conjugacy condition, so this condition automatically satisfied. So yes, so when we have an irreflexive pair, then basically we can solve the period problem. Given around the ends, the period problem is automatically solved. Then this pair, where these are the poles of the this form, this actually gives an Western data for the P genus minimal surface. It is also a complete minimal surface and finite total curvature. Okay, so so this is done. So now we have to choose proper candidate. Then we can check if such irreflexive pair exists or not. Okay, so since Fujimori and Soda already solved the genus 1 case, from there we got this pair of E-generalized orthodisk. So these are their images in C, the corresponding polygons, and from there we can actually generalize formally to the P genus. We don't know if such I mean, yes, we can draw always a polygon like that, but along, I mean, in that, is there any conjugate one or irreflexive one? We don't know. It's just the formal data. Okay, so if we do that and get the formal divisors, then we see that yes, this should be our candidate. Okay, so before going any further, I want to define a geometric object, which we are calling staircases. So just have a look at this shape. We're just copying this shape by alternating angles. So pi by 2, 3 pi by 2, pi by 2. And here, look at this shape. We're copying this shape and attaching them such that the angles are alternating. So these shapes are called staircases if the initial angle for this is pi by 2 and the end angle is pi by 2, and for this 3 pi by 2. Okay, and we also assume that these staircases are symmetric about the line y is equal to -6. Okay, and further we define the length of the staircase for a genus P staircase. We have P minus 1 number of blocks. So these are called staircases. Okay, so now we already had a irreflexive orthodisk for genus 1. We denoted by lambda naught, and we had the picture. So what we do? We break the picture at the P1 and add the staircases like this. Okay, and for the genus case, so you can add high genus staircases. You can add 2 such blocks, keeping the end parts fixed. Okay. So yes. So we break it at P1 and insert a staircase of type 1, and here we are at Q1 and insert staircase of type 2. So we got these pictures, but fortunately, our chosen orthodisk for higher genus actually mapped onto these polygons. There are polygons in C. They are mapped to these polygons. Okay. Yes. So we for a pair we defined the image by Q1 and Q2. Now we collect all such orthodisk general orthodisk pairs. And we put a condition that we take all those which defines an E conjugate partial symmetry orthogonal pair obtained by lambda naught, just like we had here. Yes. So then we quotient this by the isometry, the orientation preserving isometries of R2 to remove the conformal polygon like translation or rotation, something like that. So we define that set as a T lambda naught P. This T lambda naught P actually comes out to be subspace of this topological space. This is actually discussed previously today. Where M is the sphere with 2p plus 2 punctures. Okay, and this actually it is actually more than the subspace. This is a p minus 1 dimensional submanifold of this space, and its tangent space are realized by diffeomorphism of C, which is which just pushes the edge pairs of the two different orthogonals. So we have a pair. So we have an edge of the staircase here, and the edge of the staircase corresponding edge of the staircase here. So yes. So we define a neighborhood around one of the edges of the staircase and the in the corresponding staircases. Which pushes and pulls the edges of these his partial symmetric polygons and identity away from this his neighborhood. So we take all those diffeomorphisms and of C and take its Beltrami coefficient. That turns out to be the under some equivalence relation, those set turns out to be the tangent space of the T lambda naught P. So now we take gamma j. Gamma j is a loop including two corresponding punctures. So basically, we take this and this. We take a loop. We take this and this. Take a loop. Something like that. So and define this function for each gamma j. This is the external length function. So what this actually determines, if we sum them up, this determines that how far a generalized orthogonal pair is from irreflexivity. So we can actually prove that zeta, which is in T lambda naught P, is irreflexive if and only HP of eta is 0. And actually, and also that on this space, actually, this function is proper also. So using Gardner's formula, for these j's, you can actually prove that extremal length is constant in T lambda naught P, and in the boundary of T lambda naught P, lambda naught lies there, and there this is satisfied. So from the continuity argument, we can say that in all over T lambda naught P, we have this for these three indices. Okay, and further, we can use the proof of induction to prove that in T lambda naught P, if we assume that P minus 1 genus irreflexive pair exists, then we can prove that there is a one-dimensional submanifold of T lambda naught P where this holds. So this along with this actually cancels this one, and here only one remains. What is that? This one. Okay. Now, if on that submanifold, if zeta is not irreflexive, then it has to be non-equal. If they're equal, then it is irreflexive. So we can prove that actually there are many good edges. We are calling them admissible edges. For that, we have Beltrami differential pair. So using the Beltrami differential pair, we can prove that this is non-zero basically. Then basically what you can say that this HP has no critical points on Y, but HP is proper on Y, so there must have a critical point of HP. So this is a contradiction. So this zeta cannot be irreflexive. Okay, so there exists at least one zeta for each p. So we have which is irreflexive. So the moment we have irreflexiveness, we got the surfaces, and these are the surfaces. Yes, these are the references. Thank you.
Questions?
The surfaces?
What?
These are immersed?
Yes.
Okay. Can we say if it's embedded or not?
Okay, this is not embedded. If you see, I mean, these two sides, they are going infinitely, so they would self-intersect. They cannot be embedded.
Okay.
Yeah.
And one more question. So when we do this method, we usually get branched to minimal surfaces, right? Or
No, I mean,
okay.
the thing that is depend upon, I mean, these forms. How do you choose these forms? If you remember, in my Westersenber representation, there was a condition. Yes, this condition. If we can hold this condition, there will be no branch minimum surface. So yeah, this would be this could be determined using these forms. The form I have just shown you. Yes, these forms. So you can, if you can carefully choose these forms, that won't be branch minimum surface.
Okay, yeah, thank you.
Yes.
Can I ask a question? I can wait my turn.
Yeah.
Yeah. So, Rivu, is it a constructive proof or existence proof?
Existence proof, ma'am.
Existence proof. Okay.
ma'am.
Okay. I see. You don't know what is this irreflexive pair, how it should look like if it exists?
Right now we don't.
Okay.
But
Okay. Okay.
yes,
Okay.
maybe we can get using numerical methods. But
I see. Okay. 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 All right. Thank
yes,
you. Nice talk.
thank you, ma'am.
Yeah, talk. So I just wanted to ask, where are the two ends in your picture? In the
Yes.
orthodox picture, the two sides of that polygon, is it?
Okay, yeah, I mean, no, not in the two sides of the polygon. In the polygon's picture. So if you see one of the Q naught is lying outside, see for one of the ortho disk. This is actually the catenoidal end. So yes. So yes, this is the catenoidal end. But in the catenoidal end, in one ortho that is a finite point. In another ortho that is not a finite point. That's point lying in infinity. So this is the catenoidal end, and at the infinity point, that is an upper end. Yes. From here to here.
Other questions? Okay. If not, let's thanks the speaker again.
Thank you.